Welcome. Let me tell you the story of the three trees, and it's also a tale of the four-colored gem. Combine two beautiful things in mathematics, the four-color theorem and the Euler Gem formula. So the theorem deals with graphs, finite simple graphs, and I have here the definition again of what a manifold is. A graph is a manifold if locally it looks Euclidean, meaning that the unit sphere, every unit sphere should be a sphere. And we also define a sphere using contractibility. A graph is contractible if you can take one vertex away, such that the unit sphere and the remaining part is contractible, and that's a recursive definition. This is a very simple framework for manifolds, and the geometric realizations of these manifolds would of course be, real manifolds as we deal in classical mathematics. But it's all formulated within graph theory, and so this is a nice category. There are 0 is the initial object in that category, and 1 is the terminal object. I mentioned the theorem already last time. The arboricity of a two-dimensional sphere is 3, and I actually had hoped that the arboricity of a two-dimensional manifold is 3, but there are examples. You can take, like the simplest donut already is a counterexample. First of all, there are two things in order to prove this theorem. The first is that we have to bound it from below. It cannot be 2 or 1. We cannot cover a two-dimensional sphere with 1 tree or 2 trees. And the second thing is we have to construct explicit trees, 3 trees, which cover the gem. I tried without the four-color theorem, could not do it yet without the four-color theorem. It's a heavy theorem, so it's not quite Mickey Mouse mathematics, because the four-color theorem is one of the hardest combinatorial results we know. I already mentioned the first part last time, so we have the Euler Gem formula, which for a sphere is 2. For a general manifold, it's smaller or equal to 2 by the Euler Poincaré formula. If it's orientable, it's 2 minus the genus. If it's not orientable, it's 1 minus the genus. And then we have this Dehn-Somerville relation, which is clear because every edge is just, at every edge we have 2 triangles attached. And then we can combine that, and we have 2 inequalities. And these 2 inequalities are incompatible if we have more than 4 vertices. And every 2 sphere has more than 4 vertices. The smallest 2 sphere is the octahedron, which has 6 vertices. So that's the proof. By the way, I don't know what happens in higher dimensions. That's a very interesting question. What is the arboricity of a 3-dimensional sphere, for example? I can give you bounds using also the chromatic number. I proved once a general bound for the chromatic number of a D-manifold. Maybe that can be done. And then here the second part is to show that we can cover it with 3 trees. And in order to do that, I just opt to use the four-color theorem. So we have a coloring of the vertices with 4 colors. We can do that by the four-color theorem. These are planar graphs, like the 2-sphere is a planar graph. It has no homomorphic versions of K5, and the utility graph by Kuratowski's theorems is planar. It is we can color it with 4 colors, and now we can use this coloring to construct a coloring of the edges. Maybe I just actually can use this tetrahedron, right? If you have the 4 colors, and then you can you have six edges, and what you can do is, just depending on the pairs, so we have 2 pairs. There are always 2 pairs which are disjoint, and we can color that with 1 color, another pair with the color B, and the third one with color C. There is this concept of Kempe chain, which has, become infamous in the proof of Kempe. Gave a proof in 1879, which famously then proved to be wrong 11 years later. He would found that the argument was not right, and Kempe dealt with these Kempe chains. These are chains of vertices, passes of vertices where you have only two colors, like 1, 2, 1, 2, 1, 2. Of course, you cannot connect 1, 2, 1, 2 chain to 3, 4, 3, 4 chain. That's just what we have here assumed. So that's kind of the nice thing. But if we have such a chain, we don't want to have a closed chain. Because if we have a closed chain, then we have not a tree. We want actually to have a tree. Every connected component of a forest should be a tree. Whether you partition the graph with 3 forests or you cover it with 3 trees is equivalent. We just have to find a partition with 3 forests. And so these are not yet forests because we might have just such Kempe chains. But it's no problem to break them apart. So what you can do is you can just switch one away. So you reduce the number of closed Kempe chains one by one, and then afterwards you make sure that you don't use this already changed things again, so that the argument which applied here to reduce it by 1 can be applied again and again and again. So we have an explicit construction of the 3 trees once we have a full coloring of the graph. So that's it what I wanted to say. So interesting is, of course, in general, what happens in general, even for 2 manifolds. I don't know whether there are 2 tori where the arboricity is, maybe 5. Can it be 5, or is it always, I think it's always 4, or maybe it's also 3 in some cases. So that's it's also interesting to look at the chromatology of these manifolds. I proved this upper bound. There is a famous unsolved problem, which is whether the chromatic number is of a 2 manifold is always smaller or equal to 5. Okay, let me just stop here.